The idea is that, I mean, I think it's probably most important to focus on first, looking at our periodic table and thinking about why it's organized that way and sort of like what the groups are. But really, we can kind of answer this question with the question, what do atoms want? What do atoms want? And if you're not exactly sure what I mean by this, maybe you can think about some atoms that we consider to be quote unquote content, quote unquote happy. They're, yes, exactly. Okay. A full, and I'm going to now kind of change this to be valence shell. What does valence shell mean? Good. Of what? Good. Yes. And so the valence is like the outermost one. Okay. So they want the outermost one to be full. Okay. Well, for ones that have, like if your outer shell looks like this and you just have one little electron hanging around, right? That or that, it's reasonable that you would sort of want to do things one way versus having something like 6 or 7. Okay? So what is the difference in how these two groups, the purples and the greens, how do they accomplish a full valence shell? Good, good. So wait, how are losing electrons? How are losing electrons going to accomplish a full valence shell? Won't that be an empty valence shell? Yeah, then yeah, no, there's no electrons in there, so you have to go one more to say your outer shell, right? It's the outer shell that still has electrons in it, right? So the trick is you sort of totally empty that one. If it's these are kind of like extras, right? And here we need the extras, so that's a little bit more rational way to think of it. So we gain electrons here to get to our total of kind of getting to a full, right? Okay, cool. Who are these two groups that I'm describing here? Who are the greens and who are the purples? Simple, simple, common names for these two things. Or at least, yeah, yeah, basically, right? Nice. Okay, so who's who? Yes, good. Good. I'm going to say they become cations and they become anions. Is that okay? What do I mean by become? Beautiful. Yeah. Good. Good. And cations are positive or negative? Yeah. Awesome. Okay. So, this sort of so the best so for the most part, if we can find something that will just give me electrons and satisfy what I want, then they prefer that. For the most part, atoms are restricted to bond with other atoms and come up with negotiations, right? The negotiations are the bonds. So the best type of bond, or the sort of like you know simplest or classic type of bond, is a ionic bond. What does it mean to be ionic bond? Yes. Good. Okay. Can we say that this is a loser and a gainer kind of helping each other out, right? Both accomplishing each other's tasks for them, right? Okay, so this is between, and in fact, do we know? Because cations and anions, in fact, some things can become both. Some things can't, can't become cations, but they can become anions and whatever. But all the things that, can become cations, for the most part, we're going to put in one category. What are we going to call them? Yes, nice. So the simplest idea is a metal and, yeah, the nonmetals are the ones that are close to those, close to full shells that are way over on the right, like iodine, nitrogen, chlorine, carbon, oh no, I already said nitrogen, phosphorus, sulfur, bromine, right? All these classics, right? All of the interesting ones, okay? So, okay, ionic bonding, and what is this? Network? Okay. What is ionic bonding like defined by? What is it? How do we know it's ionic? Or maybe can you give me an example of something that does ionic bonding? Beautiful. Good. The Na does what with its 1 electron, and the Cl does what with its 7 electrons? Yeah, good. So this is a full give and take of the electron. Okay, it's a full give and take. This is important that it's a full give and a take. Okay, it's a full give and a take. So it's 100% of the time you have it and I don't. That's a full give and take. Okay. So this is the sort of perfect thing. If you're a metal, you're looking for a non-metal to be able to do this with because it's a full give and a take. They're looking to give away what you're looking to take. So it's like, you don't even need to pay somebody to do this something, right? Okay. That's not always, and almost, it kind of makes for boring chemistry because typically the atoms have found the thing that they're happiest with, so they just kind of chill. Okay? So things like rocks and things like salts and things like that last a long time, those things are a lot of them are ionic. They're ionic compounds. Okay? Because those atoms are kind of like, they're done playing the game of negotiating to try to fill their valence shell. They found their perfect mate for ionic bonding. Okay? So for those that haven't found their perfect mate for ionic bonding, what are the alternatives? If you're a cation, or sorry, if you're a metal, so a metal that doesn't ionic bond. So for whatever reason, it doesn't meet a giver, or sorry, a receiver, because a metal is a giver, right? What can it do? Can it do anything? What's that? Yes, good. Yes, so it can do metallic bonding. Awesome. What else? I mean, it can do, some depending on the kind of conditions that we put it under, we can get it to do anything. But the key one is, are we going to get it to do the other type of bonding, covalent bonding? Can we get a metal to do covalent bonding if it can't do ionic bonding? We can't. Can't actually. So covalent is, it means sharing. Okay? The metals, are they interested in sharing electrons? No. The metals, their life story is, oh, I got to get rid of these electrons, right? If somebody comes up to them and says, hey, do you want to share these electrons with me? They say, no, 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 I'm trying to get rid of electrons. Like, don't come at me with more electrons. I'm trying to share, right? Whereas the non-metals are living their life like, ugh, gotta get some more electrons. So somebody comes up and says, do you want to share? I can't give them to you, but do you want to share, right? They say, oh, okay, it's not perfect. I would prefer an ionic bond where somebody will just give it to me, right? But if you're willing to share, okay, maybe I'm willing to talk, right? So, okay, it's important that we're kind of like, and I'm doing it in my language. I'm talking about the hierarchy of ionic versus covalent bonding, right? If you're an atom, in terms of kind of like what you want, quote unquote want, obviously that's kind of like anthropomorphizing it, but you want ionic bonding because that's the kind of like best give and take. If you can't get that, you'll take covalent bonding, but not if you're a metal. Metals aren't really interested in sharing electrons, okay? So, non-metals, they do not do covalent bonding. So non-metals, they pretty much only do metallic bonding, or they just become a free ion and they just give their electrons to the environment. But you can't just take an electron from the environment like willy-nilly. You have to get it from somewhere, right? So, so it's a little tougher for anions. So they do sharing, okay? So covalent bonding is a sharing constellation in nonmetals. Okay, so what it means is, what we're talking about is this sort of circles around atoms. Let's say, for example, we have two chlorines. So we actually do this. Can you see the difference between those two, or should I make them? Is that a little easier to tell the difference? Yeah. So the green is sort of like the first chlorine, and it had its own 7 electrons. Okay, so that's chlorine with its 7 electrons. Okay, and then we had another chlorine with its own 7 electrons. Well, what are they going to do? They're going to take that last electron and each contribute 1 so that they can kind of pretend that they have 2. Because look, if you look from the green's perspective, yeah, it's including a red electron, but a red electron actually doesn't look any different from the green electron, right? So from the green's perspective, it has a full valence shell. From the red's perspective, it has a full valence shell. So but they're not actually, they're kind of sharing those two to pretend like they have a full one when they don't, right? There's actually only 14 electrons here, but they're both pretending like they have 8 to make a total of 16. Okay? So they do a covalence, means they kind of like merge their, oh gosh, that was embarrassing, their shells, right? Valence shells together. Shells to share electrons. Okay, so you can take one of my electrons as long as I can take one of your electrons and say I have 8. Okay, so that's covalent bonding. Okay, so a lot of the excitement. So these are called Lewis dot diagrams. These are called Lewis dot diagrams. This is a little bit of a part of a Bohr-Rutherford diagram. Not really. It's kind of not really anything. There's no real name for it because we don't generally do it this way, but I'm just sort of doing this to show the numbers, right? So let's maybe look at a slightly more complex covalent molecule, okay? So a covalent molecule. So let's look at the covalent molecule of let's say um, let's say NOH3. Would we really see this? No, we wouldn't. Actually, this wouldn't be covalent, so let's not do that. Let's say sulfur. Let's say SO. I think if we do SO4, we're okay. Okay, so we could do H3SO4. Let's try that. H3SO4. H3SO4. So I want to give you a second, but I want to kind of describe that as the central atom. So your sulfur is going to be at the center of things here. Okay? Give this a try. If you find it's sort of like a little challenging, then we can take a step back, or we can do this one together and then try another one. Okay? Sure. Yeah. How's it coming? Okay, so S has how many electrons? Wait, 8 outer, 6 outer, right? Okay, so 1, 2, 3, 4, 5, 6. Okay, and then O4. Where do those come in? And then double bonds here. Okay. So that would be sort of H2SO4, right? And that we could put there. All right. Okay. Is there any other way? So actually, sulfur could do this thing where it sort of has 6 spots to go at, to sit, to sort of attach at. So we should try it like that with the oxygens as well. Okay. But, okay, we're getting a little bit sort of too, so these are called polyatomic ions. Do you remember your polyatomic ions? What are they? Good. Yes. SO4 2 minus ClO3 1 minus. Yep. PO4 3 minus. Yeah, beautiful. Okay. Awesome. Yeah. So, oh yeah, sorry, yeah, I did screw this up, right? So it's meant to be 2. Okay. Okay, so okay. So not bad. I mean, that's pretty good. If you remember sort of most of that stuff in your polyatomics, there is some nomenclature stuff that, is nomenclature is how to name molecules depending on whether they're covalent or they're ionic. That I honestly don't think is like super super interesting or important for us. Like it'll be some naming that you do and you'll get back in the groove of that. I think what can be valuable to us is if we start to sort of like zoom out and zoom out and start to zoom out for some of the chemistry that you're going to do. We could also, because you also do some zooming in, and you look a little deeper and look at like some quantum stuff of the periodic table. So if you want to, we could just stick to kind of what you did last year. Um, oh yeah. Okay, yeah. Yeah, you're right. We have, right? What was it? Where was that? Was it? Okay. Okay. Um, okay. So something big then is the kind of like next step, we've done within an molecule or within like 2 atoms, within a bond. And now there might be multiple bonds in a molecule, and there might even be multiple molecules interacting. So we've kind of talked about intramolecular bonds. What are intramolecular bonds? Good. What are the types that we just looked at? Yeah. What are the intermolecular bonds? Good. These are the bonds between atoms, and these are the bonds between molecules. What are some examples of bonds between molecules? Yes, nice. Yes, nice. Beautiful. Okay, it's been a while, but it's still there. It's pretty good. Right, dipole, dipole. There's, a few different versions, but London dispersion, forces, right. Okay, awesome. So that is, um, okay, so that is a big part of kind of like where you go. I'm just trying to think about what you do. Okay, you do a lot of, as you were sort of saying, the limiting reactant stuff and things like that. So we can kind of start to look at some of that um, stereochemistry stuff, or not stereochemistry. Um, oh God, what's the word for it? Oh gosh, should forget this word. But I am. Anyway, it's like everything to do with the mole, basically, right? Um, So we can do that for the, yeah, I think that's a kind of a good idea. 'Cause it seems like your grasp of some of this earlier stuff, you still feel pretty good about some of this stuff, okay? So, and like there's a lot of emphasis on this, both in the energy section, there's two units. One is the energy section, and the other is just, oh God, what is it called? um, oh, can you think of the word that I'm trying to think of? Like the n equals m over m stuff. Yes, thank you. Oh my gosh, couldn't think of the word. Okay, beautiful. So yeah, so that's like a big, big part of the grade 12 course, and like that's kind of something that you highlighted. So let's maybe take a look at, a question that might ask about that. Okay, is that okay? Okay. Okay. So let's say that we are sort of neutralizing. We have some NH3, okay, aqueous, and we're going to add it to some HCl, okay? And we should be able to kind of predict what we produce, but in case you can't, we can maybe like talk about it. But for now, let's just say, we make something, okay? And it took, or we used, 20 grams of this and 20 grams of this. Which is going to limit us? So that is the same question as which is the limiting reactant, right? Which is going to limit how much we can make, right? How much product we can make. Now, what should the product be? Or does that not matter to this question? Well, what you, okay, go ahead, sorry. Like, what if we need, like, we haven't figured out the mole ratio, right? What if we need 30 NH3s for every one HCl that we need, right? The question is, what are we making here, right? So, what are we making? What's a possible product here? Oh, say it again? No, I mean sort of like what's the actual like chemical formula? Nice. Yeah. Okay. Good. Okay, so nice. Now that sort of answers the question of, do we need the same amount of both? Do we? Do we need the same amount of both? Do we need the same amount of both products? Same amount meaning actual number of molecules. Do we need the same number of molecules of both? Yeah. If I was going to do this with 5 molecules of HCl, I would need 5 molecules of NH3. If I was going to do this with 20 molecules, I would need 20. If I was going to do this with 30, I need 30, right? You need the same number of molecules. Okay. Do we have the number of molecules then? Is it just 20 plus 20 is 40? No, it's definitely not 20 plus 20 is 40, right? In terms of like anything that makes sense. It actually is in terms of like you can't have mass that disappears, right? But in anything meaningful in terms of moles, how will we analyze this? What should we do? Do you remember? Is it coming back to you? So let me give you a little graph or a little story that we're going to do. We're going to almost always be given the mass of something, go to the moles of that thing, use the mole ratio to say how many moles of that would go into how many moles of something else, and then from there we can go wherever we need to go. So here they're kind of, you know, they didn't really ask us about this, but what we have now is actually two things that are contributing to the production of one thing, right? So the first question would be sort of like, from A to B, how much B can I make? How much B is possible? Well, the question then, what you should ask is sort of like, how much can 20 grams get me? Well, to do that, we'll have to do this conversion, mass of one thing into moles of one thing. How do we do that conversion? Do you remember? Yeah. Yes. Nice. Good. Okay, so we can get to moles of that thing. And then what is the mole ratio to get to the product, to get to B? Yeah, if there is one, right? Yeah. And so for us, it will be the same number of moles, right? So then the question is just kind of like, can this one make more moles or can this one make more moles? Right? This is as kind of pure as the limiting reactant can be. Okay? So can the mass of A make more moles of B, or the mass of C make more? Right? That's kind of the question we're trying to ask. Okay? Okay, so let's do, I honestly don't even want to do it, this problem, now that we kind of like have the problem down, let's just do it a slightly more challenging version so that we can kind of two birds with one stone here. Okay, so let's do Br2 plus HCl produces what? How will these two things react together? What will they produce? This is definitely a skill that comes like, you know, on that sort of transition from 11 to 12. Is seeing two reactants and being able to say, okay, how would these things react together? Would the bromine want to go with the chlorine? Like what we have is a hydrogen and a chlorine. Those are two dancers, right? One's a giver, one's a taker. They're kind of like in a happy relationship, dancing together. Bromine is only one dancer. This is a single displacement reaction, right? Where bromine just comes in and swipes out hydrogen from chlorine's, you know, from under chlorine's nose. Okay? So what they're going to produce, it's going to be HBr and not Cl minus, but Cl plus, a 2Cl2, right? So that's a, you know, you basically got the idea, but I sort of like turned this into a full reaction, okay? So let's say, you know, this is the reaction, Okay? So now, let's say that I have 10 grams of this, and I have 35 grams of this. Which is the limiting reactant? Do you have an idea of how you would attempt this? Okay. So I want you to kind of always have that thread, that crumb trail that you can find, that you feel like you're on the path, right, of the question. If you do feel like you're like kind of sitting there 10, 15 seconds of like, I don't know what to do here, let me know, okay? But otherwise, I want to sort of see if you can get there on your own, crumb trail sort of thing, right? So I'll give you a minute. I'm going to mute here and I'll give you a minute and then we'll join back up again, okay? Sorry, say it again. Why? Okay, but wait a second here. Which one do we need more of? Mm, not according to how we have the reaction right now. What we're missing from the reaction right now is that this reaction is not balanced, right? So we don't have the proper mole ratios right now. So what you did accidentally was sort of said, found the moles of A, found the moles of B, and then could just compare those two. We have to go back to sort of like, okay, so how many can this make, right? Okay, yeah, it's always with a check, right? Like the worst case scenario is you just check the equation that's already balanced, right? The biggest suspect is an equation that has no numbers in it. If an equation has a 2 or a 3 somewhere, it's probably already balanced, right? But it's still worth a check, okay? Okay, go for it. Why? Okay, yeah, right? BR is actually a really, really heavy thing, so 10 grams of it is nothing, right? Okay, so the BR2 is going to limit us. Let me ask you this. Is the BR2 always going to be the limiting reagent for this reaction? Well, I mean, I guess it kind of depends on how I'm asking that question. Is everyone everywhere always going to find that their limiting reactant, not necessarily with these numbers that we're dealing with, but with this reaction, are they going to find that bromine is the one that limits them? Like it's somehow the sort of like the key one that matters for this reaction. And every reaction has a sort of like limiting reactant. And you can like look it up in a textbook kind of thing. Then what? Tell me the consequence of that. Yes, good, good. Okay, so what I was asking very poorly, obviously, was Is it particular to our circumstance, or is it a general thing that's about that reaction? Right? No, it's particular to our circumstance. We in our lab here, or in our kitchen, we're going to run out of eggs first. Some people might run out of flour first. Some people might run out of milk first. We ran out of eggs first. Okay? So that's, it's very, very, very super relatable to recipes. Okay? So make sure that you kind of like have that connection in mind. What I'm asking here is basically which one could make me more cookies, right? Or which one am I going to run out of first? Those are both, or those I guess are opposites, right? Which one's going to make me more versus which one am I going to run out of first? Okay, so I'm going to run out of BR2. Okay, awesome. Could you determine how much, so this sort of follow-up to this, or this sort of extension, is what mass of Cl2 could be made, could be produced? What mass of Cl2 could be made? As long as somewhere in there was a mole ratio to get to Cl2, right? Anytime we move from one thing, one species, one like, BR2 is one thing here, HBr is one thing here, HCl is one thing here. Every time we move between those species is what we call those in chemistry. Then we have to do mole ratio. Right? Okay, cool. Yeah, exactly. Yeah. So nothing too crazy there, right? Okay. So, okay, that's good. Sure. Sure, sure. Yeah, no problem. So what's funny about the grade 12 stuff is like you don't actually do a lot of it, but oh yeah, you're right actually. There is a section at the end. Yeah, it's actually like it's kind of crammed in. A lot of teachers kind of like just kind of throw it in at the end of the thermodynamics section. But okay. So let's talk about it. So the kind of like principal equation is that PV equals nRT. Okay? So what are all these things? P and V and N and R and T. Mm-hmm. Yeah. Yeah. Good. It's called the gas constant. Yeah. Good. In what unit? Yeah. What about moles? It's its own unit. It's a number. It's like saying dozens, right? Volume? So this is actually what this does. Depending on what unit you use for the gas constant and what number you use, it will determine the units for this. So if you use 8.314, then it's liters, kilopascals, and it's Kelvin. If you use, I think it's like 831 or something, then it's, pascals, and it's milliliters, and it's uh, Kelvin. Okay? Or ATM, right? All those different units for volume. So I could show you the table or the all the different gas constants depending on the unit that you're gonna use, but give me a minute, okay? And that's not super important. Let's just sort of see what this equation does or how it's useful or what we use it for. So what are we talking about? Like the volume of what? The pressure of what? Moles of what? Temperature of what? not only a gas, but a chamber of gas. This thing is bound, right? Okay. So, what came from this is that I could change, let's say, for example, the volume of my structure, of my chamber, right? But I couldn't only change the volume, because as soon as I only change the volume on this side, something on this side has to compensate, right? So let's say I change my volume. What would be something that I could do to change my volume? Like physically, realistically, what would I do? What would I be doing to this chamber of gas? To change my volume. Ooh, okay, you're already talking about the sort of PV equals nRT reaction. But let's just say compressing the space, compressing the volume, right? You'd be pushing the walls in, right? Okay. Let's say that I somehow had a way to keep the temperature the same. Right? Then what would I need to see? Because on my equation, I now have a PV equals nRT. Well, my V has gone down. Right? But my pressure has stayed the same. My R value has stayed the same. And no gas has left. Which means something's got to give in order for this equation to still work. If this V went down, then P has to sort of compensate by going up. You see that? Okay. We can do this with every kind of pair. Okay? So as a result, pressure increases. Okay? So let's look at pressure and volume and temperature, and then pressure and temperature. Those are kind of three interesting ones. Okay? I also want to look at temperature and concentration and pressure and concentration. Okay? Okay, so pressure and volume. How are they related? As one goes up, the other one does what? So as volume goes up, what happens to the pressure if I keep all the others the same? Yeah, pressure goes down. Good. And vice versa. Right? So pressure is inversely proportional to volume. Okay. What about volume and temperature? If I increase the volume and I keep the pressure the same, it has to, right? Which is weird, right? It's actually very tough to keep the pressure the same, which is the problem. But um, basically, as volume increases, pressure increases. So volume and temperature, or sorry, not pressure, temperature. Right? So volume is proportional to temperature. Okay, so what about pressure and temperature? Yeah, same thing. Same thing, right? Which makes sense. They're kind of, on both equals on the other side of the equation. Okay. Now what about concentration? How does concentration fit into this equation? What is the formula for concentration? Give me a concentration. Give me an example of one. Yeah. So it's N over V. N over V is something you can get out of that equation. Get me an N over V. Oh, that's a C. N over V out of this equation. What is it equal to? Yeah, P over RT. So now we can sort of see how they're related. P over RT. Okay, so as C goes up, P goes up. As C goes up, T goes down. Right? So T, as T goes up, C goes down. Are you with me on those relationships there? Okay. And this pressure goes up. It's actually probably better fitting to say this, because the concentration is really just going to be the thing that you're changing. You're going to see a change in the pressure or in the temperature. So they are directly proportional, right? So P is directly proportional to C. Okay. So those are important. And we can kind of like come up with equations from them. We could say P1 V1 equals P2 V2. And V1 over T1 is equal to V2 over T2. And P1 over T1 is equal to P2 over T2. And same sort of thing. Okay? So this we don't really do, but we could if we wanted to. Okay? Okay, so those are equations that we can use when we're talking about one gas that went from state 1, that's what the ones are here, to state 2. What do I mean by state? Went from state 1 to state 2. What do I mean by that? Yeah. Yeah. It went through a change, right? It was in one state, and then a second later we found it in another state. So what was the difference? Well, I don't know, you squeezed it down. Okay, so that's the difference between the two states, right? Yeah, that's what we mean by state. Okay. So, there are some laws and some things here, but maybe we want to see, I don't know, how are you feeling? Like, does this sound familiar? Stuff that you've sort of seen before? Okay. Okay, yeah, it's not super scary. So maybe let's just kind of like see an example. Okay. And really, we can just kind of use these equations here. Okay. So, um, actually, let me see if I can grab. Give me a second here. Okay. Oh, yeah, there's the whole organic section too. Hmm. Yeah, there's not. Hmm. Gas laws. Okay, this is a good. So keep in mind that for. Okay, wait. Actually, no. This isn't fair. We should do this example. A good idea. Yeah, okay. So let's do this. Yes. Okay, I just want to see if I can grab some strips. Yeah, let's do it. Okay. Ooh, okay, so this will give us a chance to talk about this too. Actually, let's do this one. So this is another way, maybe a more kind of test-like way we would see a stoichiometry type question. Okay. And I'm going to grab this. Let's try this one. Okay, so you might need that for that question there. How do you feel about this question here? So. Do you have a chemical reaction there yet? Yes. Beautiful. Okay. Are those the right numbers? Like, are those the coefficients that you need up front? Why, what's missing? Okay. So then, let's make that tweak. Okay, no problem. That's okay. Okay, yeah. So the key part of this is getting the equation. From there, wait, can you hear me okay? Yeah. Oh God. I'll do this. From there, we want to, we have a volume, we have a concentration, we can calculate a number of moles. From there, we should be able to use our mole ratio and calculate how much mass we need of the other one, or how many moles of the other one we need. And then we can use the concentration that it's found at to figure out the volume we need. Right? So, and if you want to, you can maybe even try these questions at kind of getting geared up for next week. Okay? Okay, so I'll give you maybe just 1 or 2 more minutes if you think you have time to try this. If not, we can just leave it here and I can send you a note and you can give these a try for next week. What do you think? Yeah, give it a couple of minutes. Yeah, for sure. Mm-hmm. Yes, good. As long as it's the same coefficient, then we're okay to jump right. Use that number of moles for the sodium sulfate, right? Okay. Yeah. And so the other thing to sort of just be careful of is 65 milliliters, right? So we want to use liters, or at least just be careful. Like you don't actually have to convert it, but just to be careful of, the fact that that's milliliters and you have moles per liter, right? Which is different. Okay, cool. So I'll send you our note either way. And then